Okay, so in this video we're going to talk about the first of Maxwell's equations called Gauss's law of electricity. We're going to talk about the form of this equation, we're going to talk about what it means, and we'll work through an example problem to help conceptualize it a little bit deeper. So here it is. This is Gauss's law of electricity. This is the integral form of the law, which states that the electric flux is equal to the amount of charge enclosed in an area divided by this physical constant, the permittivity of free space, epsilon naught. So to define a couple of terms here, we have the electric flux, which is a measure of the electric field passing through a surface. So we can also define what an electric field is, which is a condition of space, a vector field that surrounds an electric charge. So we could use Coulomb's law to help make sense of this a little bit more. So if we have a point charge drawn in space somewhere, in this case I have a positive point charge, the convention goes like this. If we have a positive point charge, the electric field lines will be directed outwards from that charge. Okay, if this was a negative point charge, the electric field lines would be directed inwards. And around that point charge, we can draw a Gaussian surface, which is a mathematical tool that allows us to ask meaningful questions, such as what is the magnitude of the electric field at some radial distance from our point charge. So from Coulomb's law, we get that the magnitude of our electric field is equal to this factor 1 over 4 pi epsilon naught times the magnitude of our point charge divided by the distance squared of the radial distance from our point charge to the Gaussian surface around it. All right, so using Coulomb's law to get a better idea of, or just kind of prove Gauss's law to ourselves, we will have to use the definition, the mathematical definition of flux, which is that the electric flux is equal to the surface integral of the dot product of the electric field vector dot the area vector. So what's an area vector? An area vector is, we could pick anywhere we want on this sphere, and an area vector is just a vector pointing outward. All right, any area vector must be perpendicular to the Gaussian surface it's coming off of. So we can go around this sphere, pick any point, and the area vector is just some perpendicular vector pointing outward. And in this case, you will see that the electric field will be parallel and propagating in the same direction as the area vector, anywhere we look on this sphere. So, to solve this integral, we simply get the magnitude of the electric field times the area of our Gaussian surface times the cosine of theta. And here theta is the angle between our electric field vector and our area vector. So now we have the magnitude of our electric field times the surface area of a sphere, which is 4 pi r squared, times the cosine. Our angle here is 0 because these vectors, like I said, are parallel and they're pointing in the same direction. So what we get then is E times 4 pi r squared. And from Coulomb's law, we know what E is. We know that E is going to be 1 over 4 pi epsilon naught times the magnitude of our charge Q divided by r squared. And then we'll tag along the 4 pi r squared, which is the surface area of our Gaussian surface. And you'll see some things canceling out. R squareds cancel, 4 pi cancels, and what you're left with is Q over epsilon naught. And we just end up with our law, with our Gauss's law of electricity. So we have the flux equals Q over epsilon naught. All right, so now we can go through an example problem, which goes like this. The electric field in a certain region of Earth's atmosphere is directed vertically downward. At an altitude of 300 meters, the field has magnitude 60 newtons per coulomb. At an altitude of 200 meters, the magnitude is 100 newtons per coulomb. Calculate the net amount of charge contained in a cube with edge length of 100 meters and horizontal faces at altitudes 200 and 300 meters. So this time we have a Gaussian surface in the shape of a cube. We have it set in the Earth's atmosphere, and we have the top of the cube with the area vector pointing upward, the bottom of the cube, area vector pointing outward, and the sides of the cube, and once again, area vector, perpendicular to the surface, with the electric field going down. All right, so if we want to calculate the net amount of charge held within this cube, we're just going to use Gauss's law of electricity, we rearrange it to solve for Q. And epsilon naught, we know what that is. That's just a constant. But we have to calculate what this net flux through the cube is. All right, so the electric flux going through the cube is just equal to the flux going through the top plus the flux going through the bottom. The reason that we do not need to consider the flux going through the sides of the cube is because our area vector on the side of the cube is perpendicular to the electric field vector. So we have a 90-degree angle between the sides, the area vector of the sides of the cube and the electric field, which gives us a cosine of 90 term. Cosine of 90 is 0, so the flux going through the sides vanishes. So we don't have to consider those terms. All right, but to solve this problem, we're just going to consider the top and the bottom of the cube, and then we'll add them together to get our net flux, and we can calculate charge. So the flux going through the top of the cube is our surface integral, and we know how to solve that. That's just going to be the magnitude of the electric field times the area times the cosine of the angle between these. If we go back to our picture, we'll see that the area vector is pointing upwards, the electric field is pointing downwards, so they're parallel but pointing in opposite directions. That means that we have an angle of 180. Cosine of 180 is -1, so we have the magnitude of our electric field. The problem says that's 60 newtons per coulomb, times the area, which is 100 meters, times 100 meters, times the cosine of 80 is -1. So we get -600,000 newtons meters squared per coulomb. We'll do the exact same thing with the top, only now we have 100 newtons per coulomb times 100 times 100. And this time we're going to multiply it by the cosine of 0 degrees because the area vector is pointing down, the electric field is pointing down, so they're parallel and in the same direction. So the cosine of 0 is just 1, and we get 1 million, positive 1 million newtons meters squared per coulomb. So the net electric flux going through our cube is just the sum of these two, of the top and the bottom, and when we add those together, you get what do you get? You get 400,000. So we get 400,000 newtons meters squared per coulomb. Now we can calculate the net amount of charge. So that's just Q equals epsilon naught times the net flux going through the cube. All right, so our constant, the permittivity of free space, if you look it up, it is, what is it? It's 8.84 times 10 to the -12th farads per meter. And we'll multiply that by 400,000 newtons meters squared per coulomb. And we get a final answer of 3.54 times 10 to the -6 coulombs. That's our final answer. All right, so how did we end up with these units? I could show some unit analysis here. So you have the permittivity of free space units, farads per meter. We had the net flux units, newtons meters squared per coulomb. And we go through the unit analysis, and what you will end up with is units of coulombs, which is our charge units. Okay, so the last thing to talk about is the other common form that you see of Gauss's law of electricity, which is the differential form. And it looks like this. We have the del operator dot product with the electric field equals the charge density divided by epsilon naught. So what we have on the left-hand side, we will term as divergence. So the dot product between the del operator and our electric field vector is called divergence. And conceptually what this looks like is that if we consider some point charge sitting in space, divergence means that the magnitude of these the electric field lines are changing as they propagate. So with some distance, with respect to some distance, the magnitude is changing. All right, and we see that in our del operator. It is equal to the x, y, and z components. So we have the partial derivative in the x direction, plus the partial derivative in the y direction, plus the partial derivative in the z direction of these unit vectors, I, j, and k. So if you take the dot product between the del operator and the electric field, you get the partial derivative, or basically the change of the x component of our electric field with respect to x, you get the change of the y component of our electric field with respect to y, and the change of the z component of the electric field with respect to z. And so to kind of have a good visual of what divergence looks like, if we have a positive divergence, that means that our electric field is increasing in magnitude with distance. A negative divergence means that the magnitude is decreasing with distance. And then we can also have zero divergence, which means that the magnitude of our electric field is not changing with distance at all. All right, that's everything I have to say about Gauss's law of electricity. The next video will be all about Gauss's law of magnetism.